Boole's inequality gives us a bound for a probability of a union. But of course, it would be nice, if at all possible, to get an explicit formula, an equality, if you will. So let's consider two events A and B again. And they're two generic events with no a priori relationship between them in terms of inclusion of one and the other. We'd like to find a formulation which describes the probability of A union B. Our approach is going to be to try to decompose events into simpler objects and then leverage additivity again and again. Right? So here are three uses of additivity. Let's start with the event A, and let's decompose A into two pieces, A minus B and A intersection B. Additivity tells us the probability of A is the sum of the two probabilities of A minus B and A intersection B. Rearrange terms, move the probability of A minus B to the left, move the probability of A to the right, and you've got an identity for the probability of A minus B in terms of the probability of A and the probability of A intersection B. We can do the same thing for the event B, decompose it as B minus A union with A intersection B. The probability of B is the sum of the two probabilities, rearrange terms, and you've got an analogous identity for the probability of B minus A as the probability of B minus the probability of A intersection B. How about A union B? Well, we can break it up into three pieces now. The segment A minus B, the segment B minus A, and the segment in the middle, A intersection B. And so A union B is the union of three disjoint pieces. Additivity says the probability of A union B is the sum of the three probabilities. On the right, we've got the probability of A minus B, the probability of B minus A, two set difference probabilities, together with the probability of A intersection B, the probability of a conjunction. Each of those set difference probabilities can be replaced by the identities we have just discovered. If you do this and reassemble terms, you'll find we'll have the probability of A, the probability of B. You'll have two occurrences of the probability of A intersection B with a minus sign and one occurrence of the probability of A intersection B with a positive sign. Reassemble everything, and now we've got an explicit identity. The probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersection B. The listener may well be forgiven for being singularly unimpressed. So what? So we did some manipulation, out came a formula. Is it useful? As it turns out, yes, indeed. This kind of decomposition has subtle uses. At a high level, what you observe is on the left, you've got the probability of a disjunction of a union. On the right, you've got raw event probabilities and probabilities of conjunctions. Decompositions like this are useful in problem settings where conjunction probabilities are easier to compute. We will see illustrations of this kind of idea when we introduce the idea, the central notion of independence. But for the time being, we've got an identity which comes out just by churning additivity. We call this identity visually, graphically, the inclusion-exclusion identity. And the idea is, if you're looking at A union B, you get to the probability of the union by first adding the raw probabilities of A and B, finding we've overcounted, and subtracting the intersection probability. We've included and then we've excluded just enough to get an identity. We can build on this further and develop other identities. The next segment is a dangerous bend segment which you could skip over at will if you wish, but shows you how we can take something like this and effortlessly churn out more identities. Before we launch into that, the reader should pause and do a sanity check. When one is given a formula like this, it is always wise to look at it from different perspectives. See if it makes sense. Does it illuminate something you already know? So, for example, you could ask, what if A and B have particular relationships? What, for instance, if A is a subset of B? What do you get? What if one of these sets is empty, or everything? What if A and B are disjoint? Play with these, see what you get, and when you're ready, proceed.